non-closed fields. So now, as I said, this non-rationality in the case of group action was in a way initiated by Bogomolov 50 years ago. And basically he just started the questions like FCN, and with the group action I consider the question is it rational or not. And so Bogomolov by education was someone coming from homotopy theory. He was a student of Novikos. And so his methods were homological, and then so this was studied by Saltman and Kuryotinen and with more refined methods. But I think that this connection between homotopy theory and the non-rationality has to be explored further, and that's one of the goals of our considerations. So we will return to this in November as well. But what I would like to talk about is a little bit different method, which is kind of related to a related question, but it's based on really Hodge theory and theory of singularities. So let's return to some example that was already mentioned by Kaiki, and this is the Delpezzo of degree 4. So geometrically, this X4 is the intersection of two quadrics in P4. So, and it is known, and you can easily compute by Riemann Roch, that every such intersection of two quadrics is birational if P2 belongs at 5 points. So one of the most studied surfaces definitely goes back to Delpezzo. Do you know who Delpezzo was? What's time? Of course, you can find this on the internet, but
19th century.
That's true, but that was there. So Delpezzo actually was a count, and so he was from Naples, and his family had a cardinal, was someone who was definitely dealing with the religious interest of the family. And so he went to visit Mitacle Flair, and so a lot of work was done in Italy, but involved a lot in Sweden. I mean, so Mitacle Flair, who was married to a daughter of a Finnish general in the Russian army, based on all this money that his father-in-law stole from the Russian army. And, today we see this story being repeated over and over again. But he did it for really a very noble person, noble reason. I mean. So he built the institute, the Tatler Flair, which is this beautiful red building that is there in Stockholm. It was built on Russian money, so this misappropriation was totally justified and created a lot of beautiful mathematics later. And so Delpezzo went there, and so a lot of this work was done there. But he fell in love with the sister of Mitacle Flair. and she was a very famous Swedish playwright. So, but she was married to a Swedish general already. And so these things were a little bit difficult in 19th century. So the cardinal had to interfere. So he got a letter from the Pope who declared that the marriage wasn't consumed, whatever that means, and so they divorced. And, but unfortunately, so Metacle Flair's sister died giving a birth to the child. And, it's a little bit of unfortunate story, but that's the story of the person who introduced these surfaces, and of course, I mean, he mainly looked at them for algebraically closed field. So now, and therefore, they're rational. So if you want to study this thing, these surfaces over algebraically non-closed fields, the story is much more complicated. And so the person who did a systematic study of this was Manin. And so Manin's approach was indeed rather systematic. And so as I mentioned during the talk, I mean, so there were a lot of works done after Manin by his students. But in this particular case that was mentioned, so Manin looked at the case when, so you see this here, the huge Picard equal to 6. But when Manin look at the case over the field, so we take X4 for a field F, so the Picard of this is equal to Z2. So it's a conic bundle. And so as you can easily compute by, so meaning it's a vibration over Q1 where generic fiber is a conic, and then you have, so it's A minus the degree, is the number of the singular fibers by Newton formula. So you have 4 singular fibers. And so here Manin comes 60 years ago with a criteria for non-rationality. So basically, so he considered this linear system. So this is the canonical class from Q1. And so this linear system is not empty, and this thing is not rational. So this is a very famous 2ks plus c invariant, which is not proven even in dimension 3, but this is how it starts. So basically there is a conjecture that in dimension 3, this thing not being empty, with the exception of one case, is if and only if condition for the non-rationality of conic bundles in dimension 3 is not proven. So a lot of people work on it, very good work, including Kohler, Mori, and so stuff. So, but in dimension, in our example, we can easily compute this because so we have 2 k of P2, sorry, P1 plus 4 points. So k of P1 is minus 2 points, 2 times minus 2 plus 4. So this is all over Q1. So this linear system is certainly not empty. So that thing is not rational. So it's a zero calculation. So now let me look at this from the perspective of the, so the is 19, it's 20th, 21st century. So now These Delpesos have very well understood their symmetry. You don't even need to think about this. It's enough to say Gromov-Witten theory. But in fact, I think one day, if I understood what Gonzalez was talking about in combination with Giritani's work, we can actually strengthen quite a bit this Burnside invariant, but this will be discussed later. And so what you can say is that this X4 has a mirror, and singularities in this case are, so I mean, it has it's a vibration of over C with several, actually with two singular fibers. Let's say two singular fibers. One is has singularity of type D4, and the other is just ordinary double port. And so now, you see this has a huge Picard, and if you restrict ourselves to the case where this Picard is D2, so if we are on the complex numbers and we allow ourselves to move in the whole so-called Frobenius manifold associated with this singularity, you can always split it to ordinary double points. And so these ordinary double points are the one that correspond to blow-ups in this picture. But because Picard is actually Z2 only, you have no way to deform any further. And in fact, you can associate an invariant with this, which is the spectrum of the singularity. And so the spectrum cannot go down to zero by deformation. So if it's bigger than zero, these surfaces cannot be rational. So I'll explain this in detail next time. So once again, I mean, the equivalent to this thing here is the fact that you don't have big enough Frobenius manifold to deform this singularity. So similarly, this example that that Kaiki was mentioning, what was it, cubic with 10 is too many. Of course, we can do it, but let's do just 2. So let me. So this is where I'll do 2 over algebraically non-closed field. So now you should understand that if you have a cubic with one 3-dimensional cubic with just one singular point over the complex number, this is rational. You all understand that. This goes back to Archimedes. So this is your singular cubic. If you have singular point, you can have a 1-1 projection to P1. So if you have 1-to-1 map, so it's birational and biregular to P1. That's true in all dimensions. But now, if we are over this algebraically non-closed fields, and these points are not defined over this field, well, then we cannot do this projection. So it's getting a little bit more interesting. And so once again, the way to deal with this is to use mirror symmetry, but in fact, you don't have to. just dealing with spectra is enough. And so, so let me, so I'll guess what is the proof of this fact classically, although guessing, but so how do we prove this, that cubic with 2 points over algebraically closed field is not G rational? So I'm guessing how the proof would go here. So let's say that I have this cubic and I have 2 points. And so there's a group acting. And so we are going to show that this is not G rational. I would expect that if you have these 2 points, there is a line passing through them, and then this has a conic bundle structure over P2 with curve of degeneration, curve of genus 3. So it's curve of degree 4. And then that produces an intermediate Jacobian, but there is some torsion on it, and that's how the non-rationality might be proven. So, but I mean, let me do it from this perspective, but what I'll be trying to prove is that what this algebraically non-closed field, so I have 2 points not defined over it. So I have a cubic with 2 singular points. Over algebraically non-closed fields. Algebraically non-closed field. So now the statement there is that there are 2 spectra. One is the non-commutative spectrum, which is equivalent to the Stimbring spectrum. Associated with the Mixed-Watch module of the Landau-Ginzburg model. So that's it, one statement, but so forget this part, but it's kind of instructive to think about it. So the mirror of this cubic without singular points, it's a vibration of K-T surfaces, which has 3 singular fibers. 2 are ordinary double points, and 1 is a very complicated one. So now this is lovely thing, which is called conical transition. But in mathematical terms, this is just that creating a singular point on the cubic, actually in dimension 3, is pretty much like creating of a singular point on the Landau-Ginzburg model. And so this would actually correspond to just contracting any of these curves. If you have a group action, you can make them correspond under the group action. And so now, if this is done over the complex numbers, so this contraction actually leads to a new singularities of this type. And then if you have no abstraction of deforming this singularity here, which carries quite a bit of spectrum, then eventually what you are going to get is just conic bundle with curve of degeneration, this genus 4 curve that you see here. So it is rational, which is a different way to see this fact that all vectors measures. But if you don't have enough space to deform, and that's precisely if you consider this Picard to be, let's say, 2, in this case, if you don't have, I apologize, if you consider this modular space to be of small dimension, the modular space of cubic is the 10-dimensional, but if you put restrictions due to the field, and you don't have space to deform, so then you'll have a hard time getting rid of this spectrum here if you don't have direction to deform, and then that gives you the non-rationality. So in particular, if you have 10 points, let's say, so the modular space of cubic is 10-dimensional, but if you have 10 singular points, and so this means that you kind of get rid of all these curves here. So, but there is no other direction in which you can deform in order to get rid of this spectrum here. So that's why in this situation, cubic over this algebraically non-closed field with the condition that you kill this modular space, it's going to be not rational. So the cubic is actually a harder example that works better in higher dimensional. So one can show that, I mean, quartic with algebraically non-closed field with enough singular points is always going to be not rational. And similarly for quartic in dimension 4 and quintic in dimension 4. So for quartic that wasn't known, for quintic that is published result of the Fernex. So in any case, so what I'll plan to show next time is what are the invariants involved here. And so how they can be computed. So now this is different from this Chinkel approach, but I think that combining them, one can actually get much stronger result in this area of algebraically singular funnels over algebraically non-closed fields. So to return to your question of the four-dimensional cubic, I think that this method actually could show that if you have a cubic with two singular points which are extended by the Galois group of the field, exchanged by the Galois group of the field, that cubic is not going to be rational. So 2 points which are not defined over the field and exchanged by the Galois group, that thing is not going to be rational. And some other similar results for four-dimensional cubic with some configurations over algebraically non-closed fields can be obtained as well. So now it is possible that this H1 actually plays a role. H1 of the group over the Picard, which is going to be very small, plays a role in this consideration as well. I haven't figured out what exactly it is. So these are the examples, but I need to show you the general method, what are the invariants that are used here. And so I'll start with this next time. But it's again, I mean, Hodge theory, a little bit more um, involved type than the spectrum of, I mean, models. But I mean, if you don't like Landau Duisburg models, you can just forget about this. And, just what you get by growing with them is going to be enough. As I said, I'm quite hopeful that someone can develop this equivariant ground Whitman theory, and then should be able to combine two things. So this Burnside approach of Jenkins and company, and then this atoms that are going to appear in ground Whitman equivariant theory. So, I mean, if you give this, I mean, I will say what is the statement, what can hope for. I mean, this certain, I mean, I'll say what's proven, but this invariant splitting is not something that is known, but if it is, then so the way to approach this problem is all right. So you have certain splitting for level of mod, and then you know what are is absolutely, how do you call them, absolutely incompressible or
absolutely incompressible.
yeah. So let's say that you're in dimension 3 and you want to study this question about genome and the genome rationality. So you need to